Okay, I suggest we start. The last talk of today is Jim Al-Khalili, who is going to summarize the discussions of the day today. You are from University of Surrey, as everyone knows.
Thank you. Okay, well, good afternoon, everyone. So summary talks are strange things, aren't they? I didn't prepare, I don't have slides, but I was scribbling away frantically in my notebook. So if I can read my handwriting, I might be able to summarize everything that we've heard today. It's just looking at the list, the titles of the talks, one might not immediately see the connections in between the different subjects. But time and time again, even if the speakers themselves didn't actually state it, I think many people in the audience would have been making these connections, saying maybe people using different terms, different words for things, but talking about very, very similar concepts. But it's been a wonderful day, a nice way to spend a Saturday. I mean, we've missed the FA Cup final, but that's fine. Probably maybe the current audience here, maybe not so bothered by that. So I want to sort of go, I will just basically methodically go through our speakers' talks and summarize what I got from their talks, what I felt was most interesting and most important. Of course, we began the day with Philip Hawkey talking about the origins of this notion of chaos in Greek mythology. I'd heard of Hesiod, but only as a name. I didn't know anything more about him. I didn't know that he was a poet contemporary with Homer. Of course, Homer's much more famous, and Hesiod's theogony is nowhere near as famous as the Iliad or the Odyssey, of course. But Hesiod seems to be the person who, as far as we know, gave the first theory of cosmogony. Cosmogony or cosmogony? I guess Philip says cosmogony because it comes from the Greek, the gamma. I probably would pronounce it cosmogony, maybe I'm wrong. But this idea that the universe grew out of chaos is something that has its origins deep in Greek mythology, 5 or so centuries BCE. Chaos being what gave birth to all the gods, the genealogy of the gods. Unlike chaos in physics, the chaos that we heard about in the later talks, Hesiod's chaos is presented without physical properties. It's a person in that sense, as a god, but also some scholars interpret this chaos as being the origin of the universe, the origin of space and time themselves. Well, a little later, after Hesiod, come people like Pythagoras. I wrote the first person to refer to the heavens as the cosmos, and Philolaus. Philolaus, is that right? Philolaus? Is that more or less right? When no one's saying boo, that's an awful pronunciation. But I answered that as far as Philolaus is concerned, he brings this notion of harmony, the order that emerges out of the initial chaos. What I also found interesting was that Philolaus's cosmology is rather different from the later Greek cosmology of Ptolemy, the heliocentric model of the universe, because he has the Earth and the Sun and the Moon and the planets and the stars all orbiting around Zeus and Mount Olympus. So it's this Zeusocentric universe, I guess. My take-home message, I think, from Philip's talk is about the idea that as far as the ancient Greeks were concerned, it was order emerging from disorder, right? The opposite to what we now think of in terms of starting with a highly ordered, low entropy universe, what people working in cosmology call the past hypothesis. The universe had to have low entropy, had to have high order, and because of the second law of thermodynamics, entropy increases. And so it's order giving way to gradual disorder. For the ancient Greeks, it was the other way round. Okay, then we move on to Chris Budd's talk. He talked about chaos first in celestial mechanics, then bring it more closer to home and talk about the weather and climate prediction. Chris starts by defining science as the search for order and pattern, which again is a recurring theme in the other talks as well. Of course, Chris gives us some history, but he jumps 2 millennia from the ancient Greeks to the birth of modern science and Galileo. Galileo found that the laws of physics were predictable. So we all learn at school about balls rolling down inclines and so on, and the fact that an object accelerates as it falls. Newton followed on from Galileo and really mathematized these equations of the dynamical laws, equations of physics. I have an interest in medieval science, and one of the things I looked into was who were the first people to mathematize physics. And people like Al-Hazin, Ibn al-Haytham in Arabic, was really probably the first person to literally mathematize the celestial mechanics and the nature of light and so on. I also was reminded of him when someone showed the circular billiard table example. Al-Hazin also studies that. But he doesn't talk about billiard balls, of course. We're talking about the 11th century. He was talking about light reflecting off circular curved mirrors. And of course, you do get that sort of chaotic behavior. You get that dependence on precise initial conditions. If you want to predict, what's the point on the mirror that would allow the light beam to bounce back to a particular, reflect to a particular position. And Al-Hazin develops a quartic equation and solves it with geometric methods like conical sections and so on. So that these ideas of mathematizing science go back actually a lot earlier than the modern scientific revolution in Europe. Chris then arrives at the dynamics of the pendulum, the idea that we can solve the equation and predict the future. For some reason, it never occurred to me that the square root of little g is pi. But yeah, great. So, as you say, in SI units, a 1 meter long pendulum takes 1 second to swing from one side to the other, a period of 2 seconds. So I'll have to try and remember that. You all knew, right? It was just me. But the nice thing here is that this notion that mathematizing the laws of physics and coming up with mathematical equations that make predictions allows us to learn something new. And Chris brings in this example of discovery of the outer planets, the Herschel's discovery of Uranus, which then, its orbital motion doesn't follow what is predicted by the mathematics, leads scientists to suggest there must be something else perturbing its orbit, something else that's affecting it gravitationally, and that, of course, leads to Leverrier discovering Neptune. The power of mathematical prediction here is really profound. But I'm also reminded of something that I teach first-year undergraduates in physics, where I teach them relativity theory, and the advance of Mercury's perihelion being the one of the first proofs that Einstein's general theory of relativity is correct. He applies it to the precession of Mercury's perihelion. So it's orbiting in an elliptical orbit, and that elliptical orbit, like a spirograph, very, very slowly rotates. And the equations of Newtonian mechanics don't exactly agree. It's something like a few tens of arc seconds per century out from what is actually observed. Firstly, it suggests, what incredible accuracy the astronomers could make in measuring this experimentally. But also, the mathematics also made a prediction there that there must be something else perturbing the orbit of Mercury, and they hypothesize a missing planet, the planet Vulcan, long before Trekkies, an invisible planet on the other side of the sun to the Earth, so therefore we never see it. But of course, gravitationally, it can influence Mercury's orbit. So here was an example where the maths didn't predict something new, but our theory of physics wasn't accurate enough. Newtonian gravity wasn't accurate, and we had to wait for Einstein's theory of gravity to resolve that problem, as indeed it did. Chris then comes on, it talks about Laplace's demon, and the notion that as far as Laplace was concerned, we live in a fully deterministic universe. Of course, Michael goes on to explain that because we can never know the initial conditions exactly, physics can't be completely deterministic. But Chris moves on then to less exotic area, namely the prediction of the weather, and give you simple examples of chaos theory even before you get to the complexity of the weather, even something like the double pendulum, which we all had fun trying to predict, when it would stop, the lower pendulum would stop going round the upper one. That, again, is a perfectly beautiful example of chaotic behavior emerging from such a simple system. And of course, famously in history, Poincaré tries to win this competition set up by the King of Sweden to try and predict the motion of the planets. And he realizes not only can he not do that, he can't even predict the three-body problem. If he just ignores everything apart from the sun, the earth, and the moon, it's still not an exactly soluble problem, the three-body problem. By the way, I interviewed the Chinese sci-fi writer Cixin Liu a few weeks ago, the author of the three-body problem. I interviewed him not having read his book. Isn't that awful? I read a summary of it. But I guess it's quite hard going. I think his second and third book are more sci-fi, sort of traditional. Anyway, that's a complete aside. Chris goes on to talk about the advances in the middle of the last century in studying the climate, studying the weather. People like Mary Cartwright and Ed Lorenz. And went on to talk about chaos in weather, in climate prediction. And here's where, there were terms that come in that I remember from undergraduate physics: strange attractors, bifurcations, and logistic maps and fractals. So it was sort of, reminded me of familiar ground that I'd lost in the depths of memory. But so thank you for that, Chris. So then we move on. So the third talk was by Ezra Sorogovan on she started off on the history of entropy. And the different ways of defining entropy. And I found, I sort of got very interested in this because there's an area that I'm currently very interested in, different definitions of entropy. We have in classical mechanics, we have, Boltzmann entropy, this probabilistic entropy, molecules of gas in a box, and they're up in one corner, and then they spread out according to the Second Law of Thermodynamics. Then you have, still in classical physics, Gibbs energy, the notion of free energy, Gibbs entropy. But of course, for me, the interest is how do you then translate those definitions and notions of entropy down to the quantum world? Things like what's called von Neumann entropy, or in information theory, Shannon entropy. So having a lovely history of the ideas of entropy and the birth of thermodynamics was very nice, from Carnot onwards. So the Carnot equation, I don't know if I knew this, but anyway, so Carnot defines this change in entropy. He talks about the efficiency. And he has an equation. He has something that he knows depends on temperature, but he doesn't know how it depends on temperature. So just some function. And that wasn't solved until later. People like Clausius and Kelvin. And that's when, sort of by the mid to late 19th century, when the whole field of thermodynamics and statistical mechanics matures. So Clausius realizes that the missing this function that wasn't understood was simply the inverse of the temperature. So you have a very simple equation that we now teach our students. The change in entropy is, delta S is delta Q over T. It's inversely proportional to the temperature. Inevitably, we arrive at one of the most famous equations in physics, Boltzmann's equation for entropy. S is K log W, so the Boltzmann's constant multiplied by the logarithm of the number of ways a state can be arranged. That's the usual way of, when I try to explain entropy to non-scientists, I usually talk about the pack of cards. You start with a highly ordered pack, all in suits and ascending numbers, and then you shuffle it, and by shuffling it, you're increasing the disorder, you're increasing the entropy. In terms of the number of the microstates here is basically the arrangement of the cards. There's only one way. Well, let's say if they were all arranged in suits in ascending orders, there's more than one way, because it depends on the order of hearts, spades, clubs, and diamonds, right? But very few ways of arranging a highly ordered pack of cards, but many ways, indistinguishable ways of arranging it once it's completely shuffled. So that idea of Boltzmann is something still profoundly important in science today. Ezra then goes on to talk about Gibbs' contribution. And it's fascinating history. So these arguments that were going on in the 19th century, Boltzmann and Zermelo and Gibbs and others talking about what does it mean, what does entropy mean, how does it fit in with the laws of thermodynamics. Well, Gibbs does this wonderful thing, as we heard, that he combines the first two laws of thermodynamics, the one regarding conservation of energy and one regarding the increase of entropy. The energy equation and entropy equation are brought together, and he has this lovely equation where the total energy of a system doesn't necessarily mean all that energy can be used to do work, to be useful. There's useful low entropy energy, and there's not very useful waste energy, okay, dissipative energy. And so Gibbs's equation says that the free energy, the useful energy that we can use to drive an engine, is the total energy of the system minus this dissipative energy that depends on the entropy and the temperature. She then moved on to talk about the application. Okay, so as I talked about applications in the real world, in industry, in economics, and even in biology. The notion, the comparison between a heat engine that takes in useful low entropy heat to do work and a living organism that takes in nutrients. It's the same thing. Those nutrients are a source of low entropy energy, right? Whether ultimately comes from the sun and feeds plants, photosynthesis, and those plants are eaten by us. And gradually the entropy is increasing, but this is still chemical matter that is a source of low entropy energy that can be used to do things. Okay, then after lunch we had Caroline Weisner talking about complexity and chaos, and she starts off by explaining that complexity and chaos are not the same thing. Complexity science, she says, started a few decades ago. There's the institute in Santa Fe in New Mexico. I guess that was Murray Gell-Mann was working there. But certainly, so that field of complexity science really started back then. But it's a hugely hot field at the moment. Certainly, when I talk to other colleagues, they link complexity with the idea of emergence. And emergence is another buzzword at the moment in science. Caroline talks about this list of deterministic rules, very simple rules that can give rise to complexity, give rise to patterns, give rise to complex structures. But what are those rules? There are rules that can give you order, structure, patterns, but there are similarly simple rules that would just give you chaos. And that led to this notion that there's a sweet spot between nothing interesting happening at all, something completely ordered, say a string of zeros, in a computer sort of data, and then on the other extreme, noise, thermodynamic equilibrium or chaos. But in the middle, there can be something interesting. There can be structure. Langton's edge of chaos, she referred to, and showed us there's this parameter lambda for a particular simple example. You can sort of play with it between 0 and 1 to go from order to chaos. But what's interesting is not the order or the chaos. It's that sweet spot that where you get critical behavior that is interesting somewhere in the middle. Now, there's criticality in nature, of course, as well as in physics. In physics, you have simple. There are examples of things like phase transitions where you get something different happening. But you see this in nature as well. And that then led to this notion of self-organized criticality, still on this boundary between order and chaos. So complexity then, she talks about as being a theory of pattern formation and self-organization. The question then is, how do you quantify it? How do you measure it? How do you measure complexity? And as I say, for me, and I may be wrong in this, but I could see all these links between the emergence of the complexity and this whole field of emergence theory, strong emergence, weak emergence, links to other hot topics like far from equilibrium, statistical mechanics, and so on. Even links to the origin of life. And notions like stochasticity, of course, as well. The necessary conditions, the last thing I wrote about Caroline's talk was listing some of the necessary conditions for this notion of self-organization. Things like feedback and memory are very important. And I still feel, because these are concepts that are not well quantified, suggests that this is still a field that is we still have many unanswered questions. It's not fully understood. We move then to our final speaker, Michael Berry, made this profound point that I will always remember and argue for, that Newtonian physics is not deterministic. Newtonian maths is deterministic. The maths is deterministic, and it leads to precise answers. You solve the equations, the dynamics of Newtonian mechanics, Hamilton's equations or whatever, you get precise answers, and you can do that, crank the handle as far into the future as you like. But in the real world, you can't do that, because no system in the real world is truly isolated. Did I get it right, Michael, that it's an electron sitting at the edge of the visible universe? Its gravitational effect is so weak, but nevertheless would influence a bifurcation of trajectory of the dynamics after 50 collisions of these balls. Yeah, I mean, but those are the numbers that we're doing. That's how hard it is to reliably predict. That's how important it is to have as exact as possible, to so many decimal places, the initial conditions of a system if you want to then evolve it in time. Michael then went on to talk about quantum mechanics, where there's a different sort of unpredictability. Well, Michael didn't talk about the various interpretations of quantum mechanics, which is more metaphysical than physical, although I think more physicists these days than before. When I was a graduate student, it was anathema to criticize the Copenhagen view, and I used to get into trouble by doing that. But it seems more accepted now that I can, I don't know what, I'm not saying I'm a many worlds or Bohmian or whatever advocate, but I'm not a Copenhagenist, that's for sure. So we won't let this go round any beyond this room, apart from the people that this is streaming to. So of course, when we talk about if Newtonian mechanics isn't deterministic, then there's additional complications when it comes to quantum mechanics, because we have issues like entanglement and decoherence, which are purely quantum phenomena. You don't get that in the classical world. And so this notion that Michael talks about, quantum chaology, is really connected with this link between the quantum classical world, the quantum classical boundary, or the transition from quantum to classical. In its simplest form, it's taking Planck's constant to zero. And you get from the equations of quantum mechanics, you'd hope to move to sort of classical equations, the Fokker-Planck equation or whatever. But that taking quantities to zero, Michael stresses, can be quite subtle. And it doesn't always lead to the most obvious conclusion. And the lovely example is, of course, the maggot in the apple, which I think brought it home very strongly. This quantum to classical boundary transition has two aspects. Michael explains that the first is this idea of reassurance. I take that to mean that you use different examples. My example is always, you don't need the standard model of particle physics to fix your dishwasher. It's the same thing, right? It's not, obviously everything in our macroscopic classical world must ultimately rely on some core theory, but you don't need that to explain the sort of higher level coarse graining world that we see around us. Decoherence theory, of course, becomes more and more important as we, there's more sensitivity to it as we approach chaotic behavior. And I think I got this right. Decoherence suppresses the quantum suppression of classical chaos, right? So decoherence gives us back the classical world and gives us back classical chaos, which the quantum world tries to suppress. There's the notion of interconnectedness, and I'll end with this. There was Michael talked about this, the staircase of the primes and the link with the Riemann zeros, and the connection between things that are abstract mathematical notions like the Riemann zeros linking to maybe something in the physical world, the vibrational frequencies of a particular quantum system. I have to say, once you started talking about the links of the random matrix theory to Riemann zeros, it's not that you lost me, it's just that I was concentrating so hard I forgot to write any notes. And luckily, for my brain, I think that was the point when I think you brought your talk to an end. So anyway, I'm pleased I took notes today. I just want to end by saying I think it's talks like today and events like today that really brings home how nice it is to have the HAP, this Center for History and Philosophy of Physics. Not every country in the world does this. There will be many skeptics, both from the worlds of history of science, philosophy, and of physics, who think this sort of coming together of these communities is never going to work, and we're not going to be talking the same language. But we do, and we're learning how to communicate with each other. I think Stephen Hawking, he may have been joking when he said philosophy is dead. I'm not quite sure how serious he was being about that. I mean, he was just being his usual provocative self, I suppose. But it's not. I mean, it's the usual argument is that, well, physicists try to find answers, but philosophers have to pose the questions. That doesn't mean physicists can't pose questions or philosophers can't find answers. But I think working together, certainly philosophers of physics, by and large, most philosophers of physics tend to have a background in physics anyway. So I'd like to think, Michael's worry that they may just want to use words. I like to think they can use the maths as well. I'll end with, I've got a research collaboration I'm working with now with mathematicians and with philosophers of physics. And I and my fellow theoretical physicists, when we talk to the mathematicians, we think, just give me the solution that fits this world, right? Not the general solution that in some abstract space. And then when we talk to the philosophers, it's just write down an equation. They can write down equations, but they prefer to talk about it. So it's been a wonderful day. Thank you all for coming, and let's hope we can arrange something else in the near future, and we'll see you all again. Thank you.
So thank you all for coming. Let me thank the sponsors, the technical team, and above all, let's thank Joanna Ashburn. All together, thank you, Joanna.